start with your integral expression for rotational inertia, which is the integral of r squared dm. And since the rod is uniform, we know that dm dr, or the rate of change of the mass with respect to the change of the radius, is m over L, and therefore dm equals m over L times dr. And you can plug that into your integral expression to get I equals the integral of m over L times r squared dr. And the limits of the integral are L over 2 to L over 2 because you're looking from the center of mass of the rod that way and that way. And then that turns into 2 times the integral from 0 to L over 2 of this expression, which gives you 2 times m over L r cubed over 3 from L over 2 to 0. Substituting in L over 2 for r, you can get 1/12 ml squared. Which is the hoop and the rod. So you add, we just found rotational inertia for the rod is 1/12 ml squared. You add that to the rotational inertia of the hoop,
put it back up,
which is
solid.
m r squared, and the r in this case is L over 2. Solving for that, you get the rotational inertia of the system is 1/3 ml squared. In part C, we're asked to find the tension in the string when a cat, which is the same mass as the hoop and the rod, is dropped from, grabs onto the string and hangs off it. So to do this, we have 2 unknowns, acceleration and tension. So I wanted to find an expression for acceleration in terms of tension so that I could plug that into this equation and solve for tension. So I used the 2 equations for torque, which are torque equals I alpha and torque equals R cross force, which in this case is the tension in the string. Solving for that, alpha is linear acceleration over R. You can plug that in, plug in the moment of inertia that you got for the entire system, and you end up with acceleration equals 3/4 tension over mass. This equation is the basic force equation. The net force equals the force of gravity minus tension. Plugging in your answer for the acceleration into here, you can solve for the tension, which is 4/7 mv. All right, part D asks for the angular acceleration of the rod hoop assembly. So again, you can use the equivalent expressions for torque, which are I alpha and R cross force, which is tension. And since we just solved for tension, and we also solved for moment of inertia earlier, we can just plug in all those variables, and you end up getting that the angular acceleration is 6/7 g over L. Then second part asks for linear acceleration, and once you have angular acceleration, linear acceleration is easy to figure out because linear acceleration is just the angular acceleration times the radius. Doing that, you get the linear acceleration is 3/7 g. The final part asks for the angular momentum of the cat around point P at the moment that the string has dropped 5L over 3. So the expression for angular momentum is R cross mv, or R cross linear momentum. We know R, we know m, we don't know v, but we can use it because we know linear acceleration. We can use our basic mechanics equations to figure that out. V squared equals your initial velocity, which is 0, minus 2 times the acceleration, which we just found, times the displacement, which we've dropped. You end up getting this for v, root 10/7 gl. Plugging that into linear momentum equation gives you L over 2 times m times the square root of 10/7 gl.